The last section of the Chapter 2, Section 2.6, talks about streamlines and sketches of fields. And in this section, they talk about looking at a line of charge as it's coming out of the page. So here I've kind of drawn an XY axis, and consider this the page of your screen or a book. And this little black dot is coming, this is the line, the infinite line of charge coming out at you. And we want to represent what the electric field is around this line of charge in 2 dimensions. And so we set z equal to a constant, or in the book's case, z equals 0, because z basically goes back that way and forward that way forever. But we're just going to look at one plane when we're doing these streamlines. And we know previously from earlier in the book that the electric field for an infinite line of charge is the rho L divided by 2 pi epsilon 0 a rho times a rho, where rho L is the charge density for the line. And so number 3 is I've redrawn this, and we have a blue line, and each one of these blue lines is roughly, it's kind of badly drawn, but around 45 degrees apart from each other. And it shows the direction of the electric field, not really the magnitude. And in the book they say you could put, if you wanted to illustrate magnitude, maybe you could put the lines more closer together, and so places of high line density would be a higher intensity. But for now we'll just say that the direction of E is given by these lines, and these lines are tangent to the electric field. And if we placed a small positive charge somewhere on this line, it would accelerate in the direction of the line. And here I've drawn out that line charge again with only just one streamline coming off of it. And what we want to find in this section is the equation that describes this blue line that I've drawn here. So what is the equation for this line? And since it is tangent, the electric field is tangent to this line, we can say the y component divided by the x component is really just the differential dy dx. Now if we go back to the equation for an infinite line of charge, and it's coming out of the screen, and here I wrote it again, the electric field intensity is rho L over 2 pi epsilon rho. And in the book they say, let's make it easy, and we'll assume that rho L is equal to 2 pi epsilon. So when we put that in there, we'll say rho, this is all rho L now. This cancels out with this, and all we're left with was the electric field for this one particular case is equal to 1 over rho a rho. And then using, now we want to find out from here, from this equation, what is EY and EX, the components in the X and of the electric field intensity in the X and the Y. And so we just always just take the dot product, AX, and then we have to look up in table 1.1 of the book and see what this dot product is, and it comes out to be the cosine of phi. And likewise down here, again you have to look in table 1.1, what is AY dotted with a rho, and that comes out to the sine of phi, and that's just given in a table. And we know rho is equal to the square root of x squared plus y squared. So I've kind of drawn out rho right here. And here's its x component and y component. And so rho here is just x squared plus y squared. And then if we want to find out what the cosine of phi is, we just use that relationship SOHCAHTOA. So cosine is opposite over hypotenuse. And I think I've made a mistake here. Or adjacent, adjacent. So this is the adjacent one. So that's x over the hypotenuse, x squared plus y squared. And then we just put everything we know in. We know what rho was. We know what the cosine of phi is. So this is cosine of phi. And then we end up with the x component equal to x over x squared plus y squared. And likewise, we do the same thing. We use the SOHCAHTOA again. So sine is equal to opposite over hypotenuse. So the opposite is this right here, y. So we got y over x squared plus y squared. And then we have, just like before here, we end up with ey equals y over x squared plus y squared. And this would, so this whole vector here, the e equals 1 over rho a rho, becomes this here in the rectangular coordinates. And then we just plug it back into our equation at the top where we said ey over ex is equal to dy dx. And we put in what we know, and this cancels out with this, and we just leave with y over x. So dy over dx is equal to y over x. We just do separation of variables and integrate, and we get this. And we could just say this constant, we could recast it and say C1 is equal to ln of C2, where they're just all constants. And then using the property of logs, the log of x times y is equal to log of x plus the log of y, we can just make this the ln of cx. And so now we have the ln of y equals the ln of cx. We exponentiate both sides, and we just end up with y equals c times x. So that's the equation for the streamline for a point charge or an infinite line of charge coming out of the plane. And then if we say, what do we want a particular equation? So find the equation for a streamline passing through as this point. X is equal to -2, y is equal to 7, z is equal to 10. Well, we don't care about the z. And so we just put in what we know. Y is equal to 7. X is equal to -2. Solve for c. And there's our streamline for just that point. So it's only for this point. That would be the streamline coming out. And then if you had like lots of points, if this was your infinite line of charge coming out of the plane, and then you would have a different c value for every one of these guys that are going off the infinite line of charge. So that concludes this chapter, chapter 2.